xp plus yq equals pq. If we depend on Charpit's subsidiary equations, when we write the given equation in the format f of x, y, z, pq equals 0, we have the given partial differential equation rewritten as xp plus yq minus pq equals 0. Call it as equation 1. Now we find out the partial derivatives, dou f by dou x, dou f by dou y, dou f by dou z, dou f by dou p and dou f by dou q in order to write the auxiliary equations. We have dou f by dou x equals p. We have dou f by dou y equals q. We have dou f by dou z equals 0 because there are no terms containing z. Dou f by dou p equals x minus q because we have to consider this term and this term when we evaluate dou f by dou p. We have dou f by dou q equals y minus p because we consider this term and this term which involve expressions of q to find out the partial derivative with respect to q. Whenever we carry out partial differentiation with respect to one particular variable, all other variables are treated as constants. The Charpit's subsidiary equations have to be written, and when we write the Charpit's ratios, we obtain dp by p equals dq by q because fz is becoming 0, and dz upon minus p into x minus q into y minus p. This is obtained by just substituting fp equals x minus q and fq equals y minus p, which we have evaluated. We have the next ratio dx upon minus x minus q and dy upon minus y minus p. When we compare the first two ratios and integrate both sides, we obtain integral dp by p equals integral dq by q, which becomes log p equals log q plus constant of integration log a. We have log a plus log b equals log ab. Therefore, log p equals log aq is obtained. When we take e raised to log p equals e raised to log aq, we obtain p equals aq, which is the equation 2. Since we have obtained a relation connecting p and q, we have equation 1 becoming q into ax plus y equals a into q square. We just substituted p equals aq here in the equation 1, and we are trying to find out an expression for q. Therefore, we have q equals y plus ax upon a. Since we obtained expression for q, we have p equals a into y plus ax upon a, which equals y plus ax. Since we have obtained p and q, we can find out the complete solution using the equation dz equals p dx plus q dy. What we did is, appropriately we will compare any two ratios in the Charpit's subsidiary equation. We will find out the relation between p and q, and we substitute the relation in the given equation, and we find out expressions of p and q such that p is independent of q and q is independent of p. Here q is the expression which does not involve any term containing p. Similarly, using this relation we could find out an equivalent expression for p independent of q. Once we have obtained such expressions, we will depend on dz equals p dx plus q dy and integrate to obtain the complete solution. We substituted expressions of p and q here, and we have dz equals y plus ax dx plus y plus ax upon a dy. When we multiply the equation on LHS and RHS completely using a, our equation becomes a dz equals y plus ax dx plus y plus ax dy. When we multiply this equation throughout using a, to this term and this term a gets multiplied, and for this term a gets cancelled. So we have y plus ax taken common outside from both these terms, and we get a dx plus dy as the other factor. When we integrate both sides, we obtain a z equals y plus ax the whole square upon 2 plus b, where b is the constant of integration. Here we perform integration with respect to variable z, that's why we obtained az. Here notice that this expression is actually the derivative of this expression. Since we write integral x dx equals x square by 2 plus constant of integration, here we have an expression along with its derivative when integrated can be written as this expression the whole square by 2 plus constant of integration. That's how we obtain az equals y plus ax the whole square upon 2 plus b, which is the constant of integration. Now we have z equals y plus ax square by 2a plus b by a when we divide both LHS and RHS using a. So we have obtained the complete solution which is defined in terms of constants a and b.